if we decide that all linear functions have a equation of the form f of x equals mx plus b, then if I take the value of m, that's my slope, if I were to start changing this value of m, what's going to happen on the graph? What does the slope tell us about the straight line that we're seeing on this graph here?
How much it varies in one direction.
How much it varies in one direction or another. Okay, so tell me more about that. You're doing maybe a hand motion that illustrates it more than words can.
Yeah, I don't know.
Well, let's try it. If I take right now the slope is 1. If I take that slope and I make it bigger, let's say I drag the slope up to 10, what do I expect is going to happen to that line? It's going to get steeper, exactly. So slope is a measurement of steepness. So as I drag this slope to be a larger number, now the line is getting a lot more steep. If I make it a smaller number, like, I don't know, 0.4, now it's really shallow. What happens if I make the slope a negative number? It's going to no longer be sloping upwards from left to right, but now it's downwards from left to right. And the more negative I make it, the steeper that downward slope gets. Right? So this m, the slope, gives us a measurement of sort of the direction that this line goes in. When it's positive, we would say that this function, this is a good calculus vocab word, by the way, for today. If the slope is positive, if the graph is going upwards from left to right, we call that an increasing function. And what was it about the slope that is going to indicate to us that this is an increasing function? Yeah, right. So for an increasing function, which is it? Positive. Right. One of the great things about calculus is that, well, let me take a step back. One of the most important things about calculus is the word slope. You'll spend at least the first half of the semester, maybe a little bit more, taking what we know about slope from looking at straight lines and trying to push it outside the box a little bit. Try to apply the same kinds of ideas about slope to functions whose graphs aren't straight lines anymore. But the good news is that the intuition that we can build by looking at straight lines is intuition that we can keep when we start talking about other functions that aren't linear anymore. So when we say today, for example, that increasing functions are those whose graphs have a positive slope, that's something that we can hold on to, even as the functions get scarier and curvy and not a straight line anymore, and the formulas start to get nastier. This relationship is still true. Okay? Having a positive slope and being an increasing function on a graph, those two will remain the same. So then, of course, for a decreasing function, what would we expect? Right. So as we can either say, as we look from right to left on the graph, our graph is increasing, or just to put ourselves on a common foundation, we tend to, at least in Western cultures where we read our words on a page from left to right, also read graphs from left to right, usually on a consistent basis. And so we'll call this function a decreasing function when the graph decreases from left to right. And the slope for a decreasing function would be what kind of number? Negative. So again, that's something you'll be able to hold on to, not just this week when we're talking about lines, but later on through the semester as we start to talk about functions that aren't straight lines, this kind of relationship will still be true. So that's what happens if we change the slope. What happens if I change the value for b? Let's say I put my slope back at 1 again. If I change the value of b, what's going to happen on my graph? It's going to shift up or down. You use the word shift, which is a very specific and correct use of the word shift, right? So my line is just moving, right? The direction that my line goes in, which is specified by the slope, is not changing. But when I change this value for b, where it's located in the xy plane is. And you called it the y-intercept a moment ago, because where do I find the value 2 on this graph? It's the y when what? So what x value is 2 associated with?
0.
Yes, right. So the y-intercept on my graph has a y-coordinate of 2, but the x-coordinate is 0, right? And so that's something also that we can take that's true about linear functions. It's also true about all functions. If I want to know where the y-intercept of a function is, what should I be doing? setting x equal to 0. Set x equal to 0 and find y. That's what a y-intercept will do for us. Right? So y-intercept means that point on the graph where x is equal to 0. All right, let me push that question a little further. How many y-intercepts can the graph of a function have?
A function, any function?
Yeah, any function. You're holding up one finger. Why?
Intercept is linear.
Okay, so if it's linear, it's only ever going to have one y-intercept. What about for any function? We make that a little more challenging. Yeah.
For each x value, there can only be one y value.
Why? How come?
Because it's a function, it's going to have an input, it can only have one output.
Right. That is the essence of what it means to be a function. Every x value may only have one y value associated with it. So the x value 0, which defines what it means to be a y-intercept, can only ever have a single y value associated with it. So we can't have more than one y-intercept for a function. Otherwise, what test would the graph fail? The vertical line test, which indicates on a graph whether we're looking at the graph of a function or not. So there will only ever be one y-intercept for any function at all, not just the linear functions. I suppose there could be 0 y-intercepts. There could be no y-intercepts at all if the function is not defined at x equals 0. But for the functions we're dealing with today, at least, they're defined for all real numbers, and so we won't have to worry about that. So that's for y-intercepts. What about x-intercepts? Let's say that I take this graph here, so the equation of this line is y equals x minus 1. What if I wanted to know what its x-intercept was? First of all, where am I going to find it on the graph? I'm going to find it on the x-axis, right? This is what it means to be an x-intercept. So looking at the graph, what would you expect the x-intercept to be?
1.
Right, so 1 would be the x-coordinate. What's the y-coordinate?
0.
Right, again, that's what defines intercept in this case, is the x-intercept is going to happen where the y value is equal to 0. So if we were finding it from a formula, set y equal to 0 and determine what x that corresponds to. Okay, so how many x-intercepts can a line have? Can have one. Does it always have one?
No.
How can a line not have an x-intercept? If what 0? If the slope is 0. All right, so you're actually jumping a little bit ahead, but I like it. So right, if I take the slope of this line and I tweak it so that the slope is, there it is, 0. Now what kind of a line do I have? Yeah, this is another big thing. Probably the most important kinds of lines. And so for a horizontal line, as you said, the slope of a horizontal line is 0. So for a horizontal line whose slope is 0, we won't be able to find an x-intercept because, in this case, our graph of our line is actually parallel to the x-axis. And two parallel lines that have a positive distance between them never intersect one another. But that's the only case in which a line can fail to have an x-intercept.